So, welcome you all in my next lecture. So, this lecture I will talk about the notion of course, I already discussed in my last lecture the notion of total derivative or differentiability of a function f from Rn to R, that means scalar field. And you know that it is not so straightforward like in the kind of real valued functions with real variable. So, it is a bit of kind of you have to think about the definitions in the like real valued functions with real variable in a different way, and then you have to somehow interpret the derivative as a linear transformation, and then the corresponding notions of total derivative I have introduced. Okay. And of course, once I have the notion of total derivative, there are some consequences you will see, like total derivative implies existence of directional derivative and partial derivative along with chain rule. And as an applications, I will talk about tangent plane and normal line for a surface. So, that is the plan. Okay. So, in my last lecture, as I said, I introduced the notion of total derivative of a functions from Rn to R, and then I said that well, in the kind of real valued functions with real variable, we know that existence, if function is differentiable at some point, it implies the continuity of that functions at that point. So, similar sort of phenomenon, whether this is true in this setting as well. Yes, answer is yes. Yes, in this setting also you do expect that if my function is differentiable, that means total derivative exists, that means it should imply that function is continuous, and answer is yes, it is continuous. I already proved that means if f is differentiable at x naught, then f is continuous. The proof I have already discussed in my kind of last lecture. So, I think I should not spend time on that. Rather, since I have the existence of total derivative and it should imply the existence of directional derivative and partial derivative. So, now I need to introduce the notions of what is called gradient. Okay. So, this is the gradient vector. So, given a functions f, say from a subset of Rn to R, where S is an open set, and take a point x naught in S, then I am going to introduce the notions what is called gradient vector of f at the point x naught. And what is that? It says that at x naught, if all the first order partial derivatives, suppose f is a function from a set A subset of Rn to R, and suppose all first order, since it is Rn, so that means I have n kind of linearly independent vectors or n coordinate axes. So, therefore, I can talk about the existence of partial derivatives in n directions, n axis directions. So, that means if all the first order partial derivatives, that means del f del xi at x naught, I running between 1 to n, if they exist at the point x naught, then the gradient vector of f at x naught I will denote by these notations, grad of f at x naught, this is the notation, grad of f at x naught, this is the notation, and it is defined by, it is a vector in Rn. And what is the first component? First component is that partial derivative of f with respect to x1 at the point x naught. Second one is that partial derivative of f with respect to the variable x2 at x naught, dot 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 up to partial derivative of f with respect to the variable xn at the point x naught. So, that means if all the first order partial derivatives, that means del f del x1, del f del x2, del f del xn at the point x naught exist, then I can talk about the, or I can give the notions of gradient vector at the point x naught. So, these are the notations of gradient vector. Various book you will have this kind of notations, del of grad of f at x naught, or in terms of language grad, grad of f at x naught, or grad of f. These are the various notations you will see. Okay. So, this is the gradient vector. So, once I have the existence of first order partial derivatives, then I can talk about the gradient vector of f at x naught. Okay. So, some examples, let us see. So, of course, I should say that if my function is like if I have a function f from Rn to R, and if my function is differentiable, that means total derivative exists, it implies that directional derivative exists, and in particular partial derivative exists, so therefore, I can talk about the gradient vector at the point x naught if my function is differentiable at x naught, in other words the total derivative exists. Okay, let us see some examples. So, like this is the functions, it is a functions from R3 to R. So, then you can easily calculate the partial derivative of f with respect to x variable, y variable, z variable at the point x, y, z. So, with respect to x variable, that means keeping y, z as a fixed constant, just take the derivative with respect to x, and similarly you do the similar kind of things for del f del y and del f del z. So, once I have the partial derivative del f del x, del f del y, del f del z at the point x, y, z, and if you say that I want to see the gradient of that functions at the point x naught, y naught, z naught, you just evaluate the partial derivative at the point x naught, y naught, z naught. So, that means you will have 2 x naught, z naught, y naught. So, this is nothing but the gradient vector at the point f x naught. Of course, this function is very nice function. So, this function is actually total derivative exists. So, in particular of course, partial derivative exists. So, and therefore, we will have the what is called gradient vector at the point x naught. So, that I have written as 2 x naught I cap plus z naught j cap y naught plus 2 z naught k cap, where I cap, j cap, k cap is nothing but I cap is a vector 1 0 0, j cap is 0 1 0 and k cap is 0 0 1. It is a orthonormal basis for the Euclidean space R3. If I have a functions f from Rn to R defined by fx is equal to norm of x square. So, you can write it explicitly, right. So, if suppose my x is say x1 up to xn. So, what is xn? So, what is this norm x square? This is actually will give you x1 square up to xn square. So, this is the functions I am talking about. So, from the given functions you can easily check that this function is very nice. In fact, the partial derivatives with respect to each xi variable exist, and you can easily calculate the partial derivative, right. So, keeping all other variable fixed, take the derivative with respect to xi variable, what will happen is nothing but 2xi for I from 1 up to n. So, that means all the partial derivative exist at any point x. So, in particular the gradient vector of f at the point x is nothing but you just put the first component is del f del x1, then del f del x2, then del f del xn at the point x1 x2 xn, which is nothing but 2x1 2x2 up to 2xn. In particular, if the point x naught is 0 0 0, this is gradient vector at the point 0 is 0. If x naught is 1 1 1, that means you put x1 is equal to 1, x2 is equal to 1, xn is equal to 1, 2 2 2. So, you can easily calculate. If I have a nice functions, if all the first order partial derivative exist at that point, then you can have the notions of or existence of gradient vector of that functions at that point. It is essential in a sense that next slides I will talk about that there is a connections like total derivative and the gradient and the direction derivatives. That is what I need, that notions actually kind of gradient vector. You will see that I will have very nice connections of the total derivative with total derivative or direction derivative. Yes. So, some properties of gradient vector, okay, del f, it says that if I have functions f from some open set S subset of Rn to R, I think this should be G, this is not f, this should be G, the typos. Okay. Suppose I have two functions f and g, okay, where S is an open set in Rn, let x naught belongs to S, and such that the gradient of f at x naught and gradient of g at x naught both exist, then gradient of f plus g at x naught also exists. It is exactly equal to gradient of f at x naught plus gradient of g at x naught. Gradient of lambda times f also at x naught exists, lambda will come out, you will have just gradient of f at x naught for any scalar. Then what can I say about the product? Product also you can talk about the gradient of the product functions at x naught, which is nothing but the value of g at x naught times gradient of f at x naught plus f of x naught times gradient of g at x naught. And if suppose the division makes sense, that means g of x naught is non-zero, then I can talk about the gradient of f by g at x naught, which is nothing but this quotient. So, then these are the properties of gradient of f. Okay, so that is the kind of all the informations if I put it together. So, this is very nice. So, this is the gist of necessary conditions for the differentiability. Differentiability means if my function the total derivative is exist. So, so if the total derivative of my functions if it exists at the point x naught, then it implies, I already kind of discussed that it implies the directional derivative of f at the point x naught along all unit vectors u exist. So, existence of total derivative implies existence of the directional derivative, and in particular existence of the directional derivative in all directions will have the existence of first order partial derivatives. However, the converse part is not true. That means existence of partial derivatives will not imply the existence of directional derivatives in all directions. Existence of directional derivative in all directions will not imply that my function is total differentiable. If you remember in my last lectures I talked about various examples. For example, this sort of functions if I consider like f of xy, which is exactly equal to say I think xy divided by x squared plus y squared. So, this sort of function if xy is 0 0 non-zero, and suppose this is 0 if xy is 0 0. If I have this function, then I already discussed that partial derivative, that means del f del x at the point 0 0 exists, del f del y at the point 0 0 exists. However, the directional derivative, that means du f at 0 0 does not exist, does not. Okay. That means existence of partial derivatives will not imply the existence of directional derivatives in all directions, and of course existence of directional derivative in all directions will not imply the function is total differentiable. For example, if you remember that functions I have considered, f of xy is equal to xy square divided by x square y4, okay, if xy is 0 non-zero, and I think 0 if xy is 0 0. Okay. So, there I have already proved that, okay, you check this function directional derivative, I think d u f at 0 0 exists in all directions. Okay. If you remember, I think this should be I think if I remember b square by a, I think if a is non-zero and 0 if a is 0. So, in the directions if u is equal to a b, if that directions, I think this is the direction derivative exists. However, these functions is not even continuous functions, these functions. This function f is not continuous at 0 0. Okay. Since it is not a continuous function, so therefore I cannot talk about the differentiability, because if the total derivative of the functions f exists at the point 0 0, then I already said it should imply the continuity of f at that point 0 0. Since my function is not continuous, so therefore it is not total differentiable, or it is not differentiable. In other words, total derivative of f at the point 0 0 does not exist. So, I think if I go back, maybe I can say these things. Sorry, let me see. I think I am sure. Yeah, look, this is the one, right. So, this is the example, right, you see. So, this is exist, oh yeah, I correct. So, this is the directional derivative exists in all directions. However, this is not continuous. If it is not continuous, that means it is not differentiable at the point 0 0, and therefore total derivative does not exist. Yes. Okay. So, therefore, that means what? That means, so then you can at least kind of guess, or I should not say guess, you can at least realize that the definitions of total or differentiability at the point x naught or existence of total derivative, that means I am looking at the changes of the behavior of the functions f in a neighborhood of x naught irrespective of the direction. That means the condition is too strong. So, once that changes, if I see, that means if the total derivative exists, that means it should implies that any directions if I see, that should also exist, in particular in the coordinate axis direction. So, this is automatic, but the converse, there are a couple of examples I have discussed where the converse is not true. So, one can ask, okay, can I put some sufficient condition so that existence of partial derivative together with that conditions should implies the existence of total derivative? Answer is yes, there are certain theorems are there that I am going to discuss in my next couple of slides. Okay. So, for example, this is a necessary condition. That means if my function is say differentiable, that means total derivative exists, then what are the consequences we will have? So, that is the theorem I have written as. So, let f be a functions from some open set S subset of Rn to R, let x naught is in S, f is differentiable at x naught, then the following thing happens. What are the things? First, the directional derivative du f at x naught exists for each unit vector u. That means directional derivative exists at the point x naught in any directions. Not only that, I can write the directional derivative of my functions f at the point x naught in the direction u in terms of the total derivative. That means total derivative I am denoting as f prime at x naught, which is a linear transformation from Rn to R, and that linear transformation should act on the vector u. So, that is nothing but your directional derivative of f at the point x naught in the direction u. In particular, all the first order partial derivative exists. Yes, if I take the directions u as the coordinate axis direction, that means all the first order partial derivative exist. And once we have the first order partial derivative exists at the point x naught, then I can talk about the gradient vector, right. So, that means the gradient vector del f grad of f at x naught exists, because all the first order partial derivatives of f with respect to the variables x1, x2, xn exist at the point x naught. Okay. And therefore, since we know that total derivative is nothing but linear transformation from Rn to R, and therefore, it will have a matrix representation. I already discussed that if I have a linear transformation from Rn to Rm, it will have a matrix representation. If I have a m cross n matrix, it will or if you have a matrix, then it will induce a linear transformation from Rn to Rm. So, therefore, since the total derivative exists, that means the linear transformation exists from Rn to R. That means I can expect what will be the matrix representation with respect to the standard basis. Standard basis means Rn has a basis say E1, E2, En, where E1 is the one component is 1, rest of them are 0, E2 is second component is 1, rest rest of them are 0, En is nth component is 1, rest of them are. So, with respect to that vector, it becomes an orthonormal basis. With respect to that basis vector, what will be my matrix representation of the linear transformation f prime at x naught? And if you do that, so this is the, so because since it is a linear transformation from Rn to R, so that means the matrix representation would be 1 cross n matrix, and since it is a 1 cross n matrix, that means it's actually a row vector or a vector in Ra. So, what would be the components? So, that means I have to give you that, okay, these are the components. So, components, since all the partial order derivative exist at the point x naught, the first component is del f del x1 at the point x naught, comma, the next one is del f del x2 at the point x naught, and nth component is del f del xn at the point x naught. So, this is the corresponding matrix representations. And once I have the matrix representation, that means when I have a linear transformation, what will be the action of this linear transformation on any vector h? This is very nice, which is nothing but the dot product of the gradient vector along with the vector h. So, gradient vector we know. So, the first component is del f del x1 at the point x naught, second component is del f del x2 at the point x naught, nth component is del f del xn at the point x naught, and you have a vector h. Suppose the component is small h1, small h2, small hn, you take the dot product. So, this is the action of the linear transformation f prime x naught at the point h. This will be useful later on, you will see. I want to write, say for example, what will be the expression of the direction derivative in terms of the, say, gradient vector. So, then you will see these kind of things there. Okay. So, what is the consequence of the earlier theorem in my previous slides? It says that if I kind of combine it, it says that suppose I have a function f from S subset of R into R, where S is an open set, and suppose you have a point x naught is in S, then what I am saying is that suppose that gradient vector of f at x naught exists, along with suppose this is 0, then I will say that f is differentiable. Now, if you remember, while calculating, when I have introduced the notion of total derivative, and then I give some example, and in fact I have calculated explicitly if my function is differentiable, what is the total derivative. Now, if you remember that time, since the total derivative I already experienced, it is a linear transformation. So, that means first I say that, okay, guess some linear transformation and then show that the limit of the quotient of norm is goes to 0. So, that guessing part, how do I do that? So, guessing part is there. Suppose you have a function f, and suppose you ensure that your all first order partial derivative exist at, suppose I want to talk about the existence of total derivative or existence of differentiability at the point x naught. Suppose you kind of convince yourselves that, okay, all the first order partial derivative exists at the point x naught. So, then immediately your guess is that, okay, the gradient vector, suppose you have a function from Rn to R, then consider the gradient vector, that means del f del x1 at the point x naught up to del f del xn at the point x naught. So, this will be your natural choice of the linear transformation. Okay, see, that is a guess. But to show that my function is actually differentiable or total derivative exists, then you have to show this object. That means limit of this quotient should go to 0. So, that is first the guessing part. Guessing part will come from the existence of first order partial derivatives. Once I have the gradient vector, then you say that, okay, this is the linear transformation, right, gradient vector. Suppose this is the gradient vector, right. So, del f del x1 at the point x naught up to del f del xn. So, that means your f prime x naught. So, this is the kind of matrix first you guess. Okay. And then you have to say that, okay, so this is the guessing part, linear transformation. But to show that my function is differentiable, I have to prove this limit should goes to 0. That means you have to estimate norm of f of x naught plus h minus f of x naught, then the linear transformation that we already guessed, which is nothing but the gradient vector, should acting on h, this norm divided by norm h, that should goes to 0 as h goes to 0, right. But what is this action f prime x naught at the point h? Just in my last slide I said total derivative of f is a guess acting on is nothing but the inner product between the gradient vector at the point x naught times with h or dot product. So, that's exactly I have written. Look, f of x naught plus h, this is nothing but this one, minus f of x naught, that's as it is. This is nothing but the total derivative, that means the linear transformation derivative of f at x naught that I am guessing, which is nothing gradient vector acting on h, and this is nothing but the dot product of gradient vector with h. Now, just you have to show that this limit should go to 0. Once I have done this one, then I will say that yes, my function is differentiable at the point x naught, and my total derivative, that means the linear transformation, is nothing but the gradient vector. That's it. Okay. So suppose I have given an example to you, so and saying that okay, calculate whether my function is differentiable at the point or not. First you check that partial derivative. Okay, so once the first order partial derivative exists, then you can guess, okay, this will probably the linear transformation that might work as a total derivative. But just because of existence of partial derivative, you should not conclude that okay, my function is total differentiable. Answer is no. We have seen an example, right? So to show that yes, this is my partial derivative exists and this is the linear transformation that might work as a total derivative, provided you have to show this limit should go to 0. That is very important. So general mistake is that, so just given a function, if I suppose give a function, I am saying that okay, check the whether total derivative exists or not at the point. So people used to do that, check the partial derivative at the point x naught and consider the gradient vector, okay, that's the total derivative exists, but this is wrong. Okay, provided if you want to really conclude that yes, gradient vector is the total derivative, you have to show this part. That means limit h approaches to 0, f of x naught plus h minus f of x naught minus that the inner product between gradient vector times any h divided by norm h, this limit should go to 0. Then only you say that yes, my function is differentiable at the point x naught and derivative is nothing but the gradient vector. Okay, now since f prime x naught, so if my function is differentiable, so this is the corresponding derivative, linear transformation, that means gradient vector. And the following expression df I have written, which is nothing but that del f del xi at x naught times dxi, this quantity sometimes is called the differential of f at x naught. So that means if all the first order partial derivative at the point x naught is exists, then I am considering the sum over dxi. So that means first order partial derivative with respect to xi variable at x naught time dxi, sum it up from 1 up to n. I am denoting as this is df, and this is sometimes called the differential of f at x naught. Couple of exercises I have given. I am not going to solve this exercise in details. It is for you. You try to solve those problems, just whatever I have discussed, whatever the concept I have discussed here. So this is one of the function. First you check whether it is differentiable at 0, 0. So first part, so that means what? That means first you have to somehow guess what will be my linear transformation to talk about the differentiability. Calculate the partial derivative del f del x and del f del y at the point 0, 0, right? So then form the gradient vector, that will be the natural choice of your total derivative, and then you show that the limit of this quotient is 0. That is one of the way. This is another example, little combinations of polynomial and sine functions. Okay, there also you show that f is differentiable. Not only that, it says that you have to calculate fx, fy that are not continuous. That means, so to talk about that continuity of fx and fy, so that means you need to calculate the partial derivative of f with respect to x variable in a neighborhood of 0. Just calculating the partial derivative at the point 0, 0, you cannot conclude anything about the continuity of fx at 0, 0. To talk about the continuity of some function at some point, you need to have the functions defined in a neighborhood of that point. Then only I can talk about the continuity. So therefore, you have to calculate the partial derivative fx and fy in a neighborhood of 0, 0. Okay, you have to, of course, you have to calculate at the point 0, 0. That's perfectly all right. Along with that, in a neighborhood of 0, 0, you have to calculate fx and fy. Then only I can talk about whether this is a continuous function or not. Okay, I think you show that it is not continuous. This is again very linear functions, g x y z, 3x plus 5y minus z. You can find the total derivative. Again, get the partial derivatives and guess your linear transformation, and then show that the limit of this quotient of norm this goes to 0. These are the, you should complete these exercises. This is not so difficult, but it is worth trying. Okay, so as I said, so once I have the notion of gradient vector, then I can have the expression of the direct line derivative in terms of the gradient vector. And you know, in the gradient vector, you just need to know what are the existence of first order partial derivatives. That's it. So that means once I have the existence of first order partial derivatives, and if I want to talk about the direct line derivative in some directions, instead of calculating through the definitions, so I will have a formula. Then with that formula I can talk about the direct line derivative of f in the direction u. So that's what it is. So suppose f is differentiable, that is a first conditions, otherwise I cannot talk about that. So that means if f is differentiable, that means if the total derivative of my functions f exists, okay, then the direct line derivative of f in the direction u is nothing but the gradient of f inner product or dot product with u. So that means if my function is differentiable, then first observation is that direct line derivative exists at that point in any direction. In particular, partial derivative exists in the axis directions. So therefore, I can have the existence everything, that means partial derivative exists, direction derivative exists in any directions. Once partial derivative exists, that means I have the gradient vector, and then the formula is that direction derivative is nothing but the inner product or dot product of gradient vector in the with u, where the directions u I am talking about the direction derivative. Okay. So, this is I am putting as a theorem, no proof is there. So, let f be a function from set S subset of Rn to R, where S is an open set, x naught is a point in S. If f is differentiable at the point x naught, then the directional derivative of f at the point x naught in the direction u is nothing but the gradient of f at x naught inner product with u or dot product to u. Okay. So, this is for any. So, that means I can have the expression of the direction derivative just if I have the existence of partial derivatives. So, that is you can have the kind of expression of the direction derivative. You do not have to go through the definitions of the direction derivative. If I know the existence of partial derivatives, that is enough to talk about the existence of direction derivative, provided my function is differentiable. That is very important, because in my next class I am going to show that this formula is not true if my function is not differentiable. That's the point. Okay. So, this is one easy example. I said, okay, take this function f x plus 2y square, it's a polynomial in x, y, z, is very nice function. This function is differentiable, that means total derivative exists. So, therefore, I can have this formula. So, you take this direction u is equal to abc unit vector and check that whether or if I take the point x naught 1 1 1, then what will be the direction derivative of f in the direction 1 1 1 at x naught. So, either you can use the direct definition of direction derivative, that you can do, else you just calculate the partial derivatives, which is easily follows from the definition of the functions, keeping other two variable fixed. You just calculate del f del x del f del y del f del z, okay, and evaluate it at the point 1 1 1. Okay, and from the what is called gradient vector and take the dot product with ABC. That exactly I have done. So, if you calculate, the gradient vector is nothing but 149. So, that means, and u is given ABC. So, that means take the inner product. This is the one. This is the directional derivative of f at x naught in the direction u. So, that is like easy way. So, to give the expression of directional derivatives once I have the expression of the partial derivative at that point x naught. Please remember that I have the assumption that my function f is differentiable, because if f is not differentiable, this is no more true. So, this is the example. Okay. So, look, so this equality need not be true if f is not differentiable. Then you can easily kind of realize, because you see a couple of examples I have discussed in my last slides. It says that some example I say that, okay, direction derivative exists, but my function is not differentiable. Now, direction derivative exists at a point in all direction, that means of course partial derivative exists. So, that means both this and this makes sense at that point, okay. Even if my function is not differentiable, then you can ask, does that equality true still now? Even if my function is not differentiable, answer is no. So, even if my function f is not differentiable, even if directional derivative exists, even if partial derivative exists, but this formula no more true. So, this is very nice. So, that is I have written, if is not differentiable at the point x naught, then this identity is need not be true. This is a very nice example. So, f of x y, again it is a functions from R to 2R. So, x y square plus y square, this is non-zero, this is 0. So, first you check that this directional derivative of f at any direction u at the point 0 0 exists, and that is straightforward. Why? Because you just calculate the direction derivative. So, how to calculate? So, check it. For example, what you have to do? So, limit t approaches to 0. Okay. So, I want to talk about the direction derivative at the point 0 0, right. So, f of 0 0 plus t times u or some direction. So, here u I think AB. Okay. So, t times AB minus f of 0 0 divided by t. So, that is if the limit exists, then I will say the direction derivative exists, but this is straightforward to calculate. Limit t approaches to 0, f of t a t b, right, and f 0 0 what? F 0 0 value is 0. So, that means divided by t. Calculate it, limit t approaches to 0, f of t a t b means what? This should be t a, then t square b square divided by t square a square plus t square b square, right, times 1 by t is there. That is very important. That in my last lecture I forgot. So, what is that? This is limit t approaches to 0. Now, you see denominator you have t q and numerator you have t q. So, everything get cancelled. So, you will have a square b square, sorry, a b square plus a square plus b square. So, that means limit exists, and which is nothing but this, and that is exactly I have written. So, I mean directional derivative exists, okay, at the point 0 0 in any directions a b non-zero. Okay. Partial derivative exists, then you can easily check, okay, that means in particular the direction 1 0 0 1. So, that means this is all, and you can calculate this is exactly 0 0. Okay. But look, I am said that, okay, this is not equal to this for suitable u. Why? So, why is that? Because this is very nice. Look, so directional derivative already calculated, it should be a b square plus b square. Now, in particular you take the vector a comma b is equal to 1 comma 1. Okay. Now, look at the left hand side. So, what will be the directional derivative? So, directional derivative in the direction a b of f at 0 0, it should be a b square, a is 1, b is 1, this should be 1 by 2 half. But what will be the right hand side? Right hand side, that this is the gradient vector. Now, gradient vector, if you calculate, this is 0 0 vector. Now, if I take the dot product with 0 0 with 1 1, it is always give you 0 0. So, this is not equal to 0, which is same as 0 0 comma 1 comma 1. So, that means this is not true. So, directional derivative exists at any directions, partial derivative exists, however, this is not true. You can check that it is continuous. Continuous also is kind of straightforward in a sense. What you say, you just said definitions of continuity, right? I am just giving a hint to you. So, what to do? So, that means you have to show that f x y minus f 0 0, right? F 0 0, you have to do some estimate. F 0 0 is 0, right? So, therefore, this is nothing but f of x y. Okay. And what is this? This is x y square divided by x square plus y square, this mod. Huh? Now, denominator is x square plus y square, which is greater equal to y square, right? So, because it is a sum of two positive square. So, therefore, which is lesser equal to mod x y square divided by y square. Okay? And this is what? This is mod x. Okay? And mod x is lesser equal to square root of x square plus y square. So, and then you just use the epsilon delta definitions. So, given epsilon, you have to have a delta, here delta is equal to epsilon, and so therefore, my function is continuous. So, that estimation itself will tell you. But this is very important, that function is not differentiable at the point 0 0. So, now you can prove it, right? Because since that gradient vector exists, so that means you have a guess. Okay, this might work as a like total derivative or matrix, right? That you know, and that already proves 0 0 vector. So, you have to just check whether this limit exists or not. Limit h approaches to 0, okay, norm of f of x naught, I am talking about 0 0. So, x naught means 0 0 plus h means hk vector. Okay, so suppose I am saying that h approaches, so that means h is equal to small h small k goes to 0 0. So, this should be 0 0 plus hk, okay, minus f of 0 0 minus the gradient vector, but gradient vector is 0 0, and 0 0 if it acts on any vector, it is a 0 linear transformation, it will give you 0. So, nothing, it will not contribute anything, it is 0 divided by norm of h comma k. That object I have to check, if this is goes to 0, limit hk goes to 0, this limit should go to 0. But what is this? This is limit hk goes to 0 0. Look, f 0 0 is 0, this is a total derivative. Our guess is that it is nothing but the gradient vector at the point 0 0, but which is 0 0 vector. So, 0 0 linear transformation, 0 linear transformation, if it acts on any vector, it will give you 0, it will not contribute. So, only you will have f of hk divided by norm of hk. So, that limit you have to check whether this is exist or not, but this limit does not exist because of the definitions of your f. Why? Because if I calculate this one, then what will happen, I am doing it here. So, limit say hk goes to 0 0. So, f of hk, so that means it should be hk square divided by h square plus k square, okay, that will be there. I think there will be a mod, okay, and you have a norm of hk, that means this is square root of times h square plus k square to the power half. So, that means what will be the denominator? That means denominator will be h square plus k square to the power 3 by 2. So, that means I want to talk about the limit of this object. What object? Limit of hk goes to 0 0, okay, my writing is very bad. So, this should be mod h k square divided by h square plus k square to the power 3 by 2. This limit does not exist. Why? Because if I take h is equal to, you just try by yourself. So, if I take h is equal to m k, this vector m is some gradient. If you come to the origin, because h k goes to 0 0, come to the origin through the part h is equal to m k. Then what will you see? So, numerator will give you what? The numerator will give you, I think, m k q, okay, and denominator also m k square, if I take the common, that means k square to the power 3 by 2, 2 to get cancelled, again kq will come. Kq get cancelled. So, you will end up with, I think, this kind of thing, mod m divided by 1 plus m square to the power 3 by 2. This kind of limit you will get, this limit, and this differ from different values of m. So, limit does not exist. So, therefore, my function is not differentiable. So, this the example says that. So, that means to have the equality of the directional derivative in terms of the what is called gradient vector and the direction dot product of the directions u with the gradient vector, it is possible if my function is differentiable, then for formula is true. But if f is not differentiable, I do not know. In some cases it might true, in some cases not, because this is the example, here it is not the case. Okay, so I think so that's all about the necessary conditions. Okay, that means if my function is differentiable or total derivative exists, then I can have the existence of direction derivative, partial derivative, then I will have the notions of what is called gradient vector. Then I have said that okay, you can have the matrix representations of your linear transformation in terms of the gradient vector, and then since direction derivative exists, there is a relations of direction derivative with the gradient vector. So, these are all about the necessary part, but of course, if my function is not differentiable, then this equality like the expression of direction derivative in terms of the gradient vector is no more true. Okay. In my next lecture, I will talk about the sufficient conditions, as I said. So, couple of examples I said that existence of partial derivative and direction derivative will not imply the existence of differentiability. Now, the question is, can I put some conditions on the partial derivative so that I can talk about differentiability? Answer is yes, and maybe next lecture I will talk about that. Okay, thank you.